So we're going to talk about the layers of the Earth. And yes, that is a Shrek joke. I know, it's about as clever as I get. Ogres are like onions, or cakes, or parfaits. They all have layers. And in the video that we just watched, he talked about why those layers are around, but we'll discuss more of that in just a minute. So the layers of Earth. All right, so we need to understand what the Earth is made out of, all right? Majority of the stuff in the Earth is these 6 elements, all right? These 6 elements. Well, elements are, it's good to know what an element is. They are just pure things that are not mixed together with other stuff. So for instance, an atom of iron, right? An atom of iron is just iron, right? It's just one thing. Here's silicon, magnesium, nitrogen, and hydrogen. But these elements aren't just all by themselves. If they were, then we wouldn't have life, right? Well, there wouldn't be much of anything, really. These elements are bound together to make molecules, right? So a molecule is 2 or more atoms that are stuck together. And there are some examples there, SiO2, FeO, H2O. I'm sure that you recognize at least one of those. So if you've ever thought about, so the entire universe, everything in the universe is made out of elements, right? Made out of atoms. What kind of elements, what kind of atoms are rocks made out of? You ever considered that?
No.
They're just rocks, right? They're just
Pieces of stone.
Pieces of stone, right? What is stone made out of? What are the elemental things in stone, right? So water is made out of 2 different kinds of elements. What 2 elements are those? Anyone? Made out of 2 elements. No? No one wants to answer? H2O, have you heard this before? Kind of. H2O stands for hydrogen and oxygen. There are 2 hydrogens and there's 1 oxygen. Rocks are made out of silicon dioxide. So silicon dioxide is this guy right here, SiO2. So there's 1 silicon atom and there are 2 oxygen atoms. That's what rocks are made out of, okay? Oh, that's not what I meant to do. There's a very common misconception that people, for some reason, think that the Earth is 75% made out of water.
It's not. That's the surface.
Right, the surface is covered mostly by water, about 75%. It's more like 68 or something like that percent. But the composition of the Earth, what it is actually made out of, is mostly rock and metal. Okay, mostly rock and metal. And this right here, this Fe. Does anyone happen to know what element that is? Doesn't make a lot of sense why it's Fe, but this is iron. Fe is iron, from the Latin ferro, which means iron. Ferrous oxide right here is iron bound to an oxygen. There's a whole bunch of iron in the Earth. Okay? So let's move on here. Well, it's important for you to understand differentiation. Okay, it's a really fancy word that just means things that are really dense sink, and things that are less dense float on those things. which is something that we experience all the time, right? If you throw a ping pong ball into a pond, the ping pong ball floats because it is less dense than the water. If you throw a piece of steel into water, it sinks because it is more dense than the water. This applies as well to the ground, to the earth. So we don't sink into the ground because we are less dense than the ground. We float on top of it. Isn't that kind of a weird thing to think of? You don't really stand on the earth, you float on it.
And we never really touch anything.
That is true. You never actually touch anything.
But then how do we feel it?
Because the electrons in if you push your fingers together, if you push your finger on the table, the electrons in the atoms in your finger are pushing against the electrons in the atoms in the table. And that creates a push that is then registered by your nerves. That's how you feel it. Okay? So lighter elements float on top of heavier ones. Who has ever heard of platinum? Few of you? Platinum? It's like a super expensive metal, right? Has anyone ever seen a ring or earrings or any jewelry made out of platinum? They are pretty interesting. Platinum is a very interesting metal. One time I actually got to hold an entire flute made out of solid platinum. I don't know why they let me hold it. It was like several $1 million worth of platinum, but pretty crazy. And this flute was made out of platinum, and I got to hold it. Platinum is really expensive because it's so rare. But the Earth has a bunch of platinum. It's just in the core. Okay? The Earth has a bunch of platinum. It's just in the core. Because when the Earth was molten, so let's recall back to how the Earth formed, right? All of this stuff was running into each other. The protoplanet was sweeping up all of the junk in the solar system. And it was actually molten. The entire planet was melted. When it was melted, the heavy stuff sank into the center of the planet. This is primarily heavy metals like iron, nickel, platinum, gold. Okay, gold is actually not rare at all on Earth. It is all just mostly here in the center. So it's hard for us to get it.
That's why we call it rare.
That's why we call it rare. Sometimes people call them rare earth metals. Well, they're rare on the surface of the Earth, but they are not rare in the core. Okay? The density, the buoyancy, so you know what buoyancy means? Buoyancy means the tendency of something to float on top of something else. The buoyancy of light elements on top of heavy elements is what causes these layers to form. And this is the reason why the atmosphere is above us and the crust is below us. We are less dense than the crust, but we are more dense than the atmosphere. If you were less dense than the atmosphere, that would be a problem.
We would die.
Because you would float away, and then you would die. Okay? That would be an issue. So we have these distinct layers. All right, questions about differentiation? That's a really fun word in my estimation, differentiation. All right, so we have that. Now we need to start talking about the specific layers, and we're going to start in the middle. The central, or sometimes called the inner core. The inner core, also called the central core. The core of the Earth is made up mostly out of iron and nickel. It is about 1,000 kilometers in radius.
What if we drove to the center of to the core of the Earth? Would the Earth explode?
No, the Earth would not explode. You would explode, but the Earth would not explode. What's up, Gracie? That is a great question. So the question for the people watching on YouTube that couldn't hear, Gracie asked the question, is there a possibility of there being materials that we are yet unaware of in the core of the Earth? Kind of, and I'll explain what I mean by that. I mean that we have a pretty dang good idea of what should be down there based on the way that the Earth behaves. And we have a pretty good idea of how different chemicals and so forth combine at those kinds of temperatures and pressures. So it is unlikely that we would find anything new because we have a pretty good idea of what it should be. But it is very possible that there might be something that could surprise us. Does that answer your question? So based on our models, we should be able to understand it, but you never know until you get there, right? Daniel?
What if we were able to get to the center? Would we get to it, the different metals, or would we not?
That is a great question. If we were able to dig into the center of the Earth, would we dig down there to go get the platinum and the gold and all those really valuable things? I would probably say no, because that would actually be really, really, really hard, and it would be easier to just go to asteroids and get it there. And asteroids have it in abundance. So asteroids didn't go through differentiation because they don't have enough weight. Okay, they don't have enough mass to pull things into the center. So they just have platinum and gold and silver just sitting on top of this asteroid. Okay, so more than likely it would just be easier to go to an asteroid than it would to dig down into the center of the Earth. But that's a great question. But we could get it, I mean, if you were able to drill down that far. All right, it's really hot, about 6,000 degrees Celsius. All right, so just for reference, that is way, way, way above the melting point of iron. Way above the melting point of nickel. Has anyone seen, like in a movie or in real life, which is a cool experience, someone forging something out of molten iron? It's pretty sweet, right? They melt the iron and then they pour it into a cast. Let's just say it's a sword. They pour the molten iron into the shape, the cast, the shape of the sword, and then you let it cool, right? That liquid iron is only like 1,000 degrees Celsius, 1,200 degrees Celsius. This is 6,000 degrees Celsius. That's the same temperature as the surface of the sun. Okay, it's really hot. So the question is, what kind of state of matter would the core be in? What kind of state of matter would the core be in if it's 6,000 degrees Celsius? What do we think? What?
A very big number.
A very big, no, state of matter. The states of matter are liquid, solid, gas, and plasma. What state of matter would it be in if it's so hot? Well, it's kind of a trick question because not only do we have to take into account the temperature, we also need to take into account the pressure. The pressure is actually so great in the core of the Earth that while it is very, very hot, and it should be hot enough to melt the iron and the nickel, the pressure keeps it solid. So the inner core of Earth is actually solid, superheated iron. Solid, superheated iron. Right? And it's 1,000 kilometers in radius. 1,000 kilometers in radius? That is huge, okay? If I was to drive 1,000 kilometers, let's say if I was driving east from here, so that way, I would end up probably in about, maybe like Kentucky, right around there, okay? So that's a lot of distance of just solid, hot iron, okay? That's pretty crazy. So that's the central core. The central core has this really cool effect called the dynamo effect, the dynamo effect. You don't need to know the term dynamo effect, but it does make a magnetic sphere, a magnetic layer around the Earth. And this is super important because it saves us from radiation hitting us from the sun. I don't know if you've had a really bad sunburn before. They're the worst. Really bad sunburns are terrible. Now imagine a sunburn that doesn't just make your skin red and make you feel uncomfortable. Imagine a sunburn that like,
Not your skin.
yeah, kind of, like pretty much destroys your skin, okay? That's the kind of radiation that the sun puts out every once in a while, but the magnetic field around the Earth keeps us safe from that. It's pretty cool. Mars didn't get so lucky with that. Mars does not have a dynamo effect. Its inner core does not generate a magnetic field, and therefore, when people go to Mars and live there, they will have to live in radiation-shielded housing. Because without that radiation shielding, they will die relatively quickly, okay? So the Earth makes this nice magnetic field for us because of the central core and how that works. Okay? Questions on that so far? Now let's talk about the outer core. So we see this image here. Here's the solid inner core. It is rotating inside of the Earth.
It is.
Well, it rotates ever so slightly faster than the rest of the Earth. The liquid outer core here is about 2,000 kilometers thick. It's 4,400 degrees Celsius, give or take a little bit. And this is where the movement of magma comes from. And we'll talk about that in greater detail in a little bit. I want you to write down as well in your notes that the inner core is primarily metal. The outer core is a mix of half metal, half rock. It's about half metal, half rock. But it's all melted, right? It's all melted. Still really hot, but there isn't enough pressure to make it into a solid. We'll get to the mantle and the crust in just a minute here. Okay. So we're going to move on here just a second. So there are things called magma plumes. Magma plumes. So here, I'm a visual learner. I don't know about all of you, but infographics like this really help me understand things. So here's our inner core. Here's the outer core. The outer core sometimes actually melts holes in the mantle and sends up these plumes of magma. Okay? Sends up these plumes of magma. I'm going to start this video actually in just a minute. Okay, so this magma plume here goes up, gets stuck, actually creates a mountain chain underneath it. Sometimes it goes through the mantle, up into the crust, and then can create volcanoes. Okay? Those volcanoes are created by these really hot magma plumes coming up through the crust of the Earth. And there's this process called convection. Okay? Process called convection that I'm going to explain to you right now in a little bit greater detail. Does anyone have any idea of what convection is? That's negative? Okay, so I'm going to pull this up here. And we're going to do one of my patented beautiful drawings. We're going to do, so this right here, we're going to do green for the crust. We have the crust of the earth. And I'm actually going to make a, oh, actually, I'm going to use, ooh, this is going to be so pretty, guys. You ready? Can I change the color of this? I don't know. I simply do not know. Probably can. All right, so we're going to make a circle. And this is going to be the earth. Okay, that's the earth. What? Well, the earth is actually an oblate spheroid. It's not a perfect sphere. So it is actually more oval shaped than circular. That has to do with a couple factors. Anyway, we can change the color, right? Aha! Let's go with green. And we'll make, yeah, we won't do the fill color quite yet. Because that's the crust. The green is the crust here. And we're going to do another circle. And this one is going to be like this. We can stretch it out a little bit, make it fill the space a bit more. This might be the best drawing I've ever done, guys, because I get to cheat with the computer. And we're going to make that one red. Okay? And this is the mantle. Okay? The mantle is, if can I do a fill color? Oh, yes. Then we have another, we're going to do another circle here of the outer core. Move that there. This is the outer core, okay? And we're going to make that yellow. And we're going to make the fill black. Oh, it's already black. Let's do the fill of this one. How about green? No, not green. How about, no, not yellow either. Whatever, I'm going to do green. Okay. So this, the mantle here, I better label these things so that you can see what I'm talking about. Mantle. And crust. Okay. Look at how beautiful this is, guys.
It is.
Aren't you proud of me?
Yes.
Good. Outer core. Okay. So the outer core is really hot, even compared to the mantle. Well, the inner core, which we're going to do, is just a black circle. We're just going to do it really small. We'll fill it with red. The inner core is the hottest part. And this outer core, the outer core here, because it's liquid, what happens is the magma inside of this, can I zoom in on this? No? No? That's weird. I zoom out and this gets bigger. I don't know how that works. Okay, so the inner core here is really hot, even compared to the outer core. And what happens is we create these convection patterns. So the magma close to the inner core gets heated and it becomes less dense. Who's heard the saying, hot air rises? Hot air rises, right? That's why, like, when you go visit your grandma's house and you have to go sleep in the attic, in the middle of the summer and she doesn't have air conditioning,
Kind of.
and it's like 20 degrees hotter in the attic than it is in every other room. That's because the hot air is rising because it is less dense. It just rises, it floats above the rest of the stuff. Well, when it rises like this, it gets closer to the mantle, which is cooler, and so it cools off. And so it sinks back down again. This is called convection. All right, this is called convection. And it happens in every direction around the Earth. And so you get these convection currents that go like that. Do you see how that works?
Yeah.
This is kind of the same thing that happens in a pot of hot water. It starts to create these convection currents. To be honest with you, I am quite proud of that drawing. I know I probably shouldn't be, but I am. Okay? Questions so far on everything? All right. I'm going to go back to this here. Okay. So the magma plumes are created by those convection currents and go up to the surface. Those create volcanoes. We'll talk about those in greater detail when we get to the volcano portion of the class. Yay, volcanoes. All right. So those, like I just said, it can create these magma plumes. The plumes go up to the surface. They break through, creating these volcanoes. In the case of, this is the Hawaiian Islands. In the case of the Hawaiian Islands, the Pacific plate, so that's the tectonic plate that is on the Pacific Ocean, or under the Pacific Ocean, is moving this way, and this magma plume comes up and creates new volcanoes every few 100,000 years. You can see that Oahu is 3.4 million years old. Molokai is 1.8 million, okay? You don't really need to understand too much about this, but the fact that it creates volcanoes. Now we get to the mantle. The mantle is right around 2,900 kilometers thick. It's plastic. We'll talk about what that means in just a second. It is mostly made out of rock. There's a little bit of metal. So you're probably seeing a trend here. The inner core is almost all metal. The outer core is about half metal, half rock. And the mantle is almost completely rock with very little metal. Again, that has to do with the fact that metals are dense, and so they sink. And rock is less dense and therefore floats on top of the metal. Okay? What do you think I mean by plastic? Does that make any sense at all?
Plastic, like you put your food in.
You put your food in? So plastic is actually describing one of the traits of the mantle, and that trait is plasticity. Plasticity. Hey, what's up? Yes, you know. Plasticity is the ability of something to be molded and or distorted. So this is a meter stick I have in my hands, yes? What is it made out of? It's made out of wood, right? But I can say that this this meter stick has a degree of plasticity because I can bend it. You see that? It has plasticity because I am able to bend it. Not a hinge. There's not a hinge right here that makes it fold over. I can bend it because it has a plastic characteristic. Okay? Plastics that we encounter in everyday life, like this Powerade bottle or this tape dispenser, these are plastics, right? Or like speaker, pretty much everything that we encounter nowadays is made out of what we call in everyday speech plastic. Plastic is the real word for it is polyethylene, but we just have given it the name plastic because it has the trait of having plasticity. The mantle is malleable. Malleable, that's a good word. It is able to be bent. This is a rock. This is solid rock that is being bent.
Well,
That's an unusual thing to think about, right? Can you imagine bending a rock? Not really, right? Generally, when you try and do something with a rock, it just breaks. It's brittle, it's fragile, right? Like if I so I have a rock right over there, it's got a fossil on it. Imagine it if I tried to grab that rock and bend it, tried to fold it in half. That'd be kind of strange, right? More than likely, if I tried to do that, it wouldn't do anything. But if I was actually stronger, then it would just break, right? In the mantle, it's hot enough and has high enough pressure that rock is bent and misshapen. So sometimes geologists will find layers of rock or large rock formations that have actually been bent and changed shape. Okay? So hot rock, but it's not melted yet. It is just really hot and thus can be molded and reshapen. Okay. Questions on any of this so far? The mantle and its plasticity. Another good word, differentiation and plasticity. Man, those are some good words. Convection. I like those words. All right, now we get to the crust. This is, of course, where we live.
It's very crusty.
True. It's also called the lithosphere. Underneath the Earth's underneath the crust, there's a portion of the mantle that is called the asthenosphere, but you don't need to know that. It's very thin. Very thin. So hopefully you all know what an apple looks like, yeah? I don't have one to demonstrate. I forgot to bring my apple this morning for lunch. I know, so I don't get to show you. But I want you to consider an apple and taking a bite into that apple. The skin on that apple is about the same thickness relative to the apple as the crust is to the earth. What about a hot pocket?
Yeah, it's got like crust, and then like a really hot, kind of hot.
Right, that's a good point. So the earth is a rock hot pocket. Sure, I get that. The crust on a hot pocket, though, is much, much thicker than the crust on the earth relative to the hot pocket, right? So that is a good idea. That's a good way to put the two together. But speaking of the size of things relative to the overall size of a part, so the size of the Earth's crust is similar to the Earth as the thickness of an apple's skin is to the apple. And the meat of the apple is very similar to the mantle And the core of the apple is actually very similar in size relatively to the Earth and its core. Okay? This, of course, is one of the most famous images of all time. Does anyone know what this image is called? It has a name. Has anyone heard of it? This is the blue marble. The blue marble. Classic image of the Earth. This image was taken in the 1970s, I think 1971 or 72, by one of the astronauts in the Apollo program as they were headed back from the moon. And from the astronaut's point of view, this was actually upside down. You can see Africa here, the Arabian Peninsula, the Red Sea, the Persian Gulf. Here's Madagascar, Antarctica, the Indian Ocean, and the Atlantic Ocean. Okay? In my opinion, that's pretty sweet. That's a really cool image. Speaking of things being upside down, have any of you seen a south up map, or what people would call an upside down map? My guess is that it's going to upset a few of you because people don't like things that they're not used to. Pretty interesting, huh? This is a Mercator projection, which is the same projection as I have on the quote unquote wall over there. Look at how it just kind of has a weird feel to it, right? Because we're so used to it. Every once in a while, I'll just screw with everyone. I'll flip both of the maps that I have here. I'll flip this one upside down and that one, just to screw with people. Because in space, there is no up and there is no down. North is not up. North is just that way. Okay? North is just a point on the Earth at which it rotates. The fact that we put north on the top of maps is actually just a consequence of the people that made the maps lived in the northern hemisphere. That's it. So they thought it was more important. I think it's cool. I love that the words are also, it's like upside down map. The Russian Federation, here's Canada, the United States, China, Kazakhstan. Also, I don't want to go on a rant, but did anyone see a couple of years ago the "Can you name a country" clip? Okay, I'll have to show it to you. It's infuriating. It made me so mad, and it really just drove home the importance of you all paying attention in school, because they interview people and they have a world map that doesn't have any names, countries on it, and they say, "Can you name a country? Can you can you locate a country?" And they can't. Not even the United States in which they live. It's so depressing. Okay, I know. We'll probably watch that video later because now I can't stop thinking about it. Okay. The crust is split into two main categories. We will come back to that later. You don't need to worry too much about that right now. There is oceanic crust and then there's continental crust. But again, you don't need to know that right now. We'll come back to it when we get to plate tectonics. This image, I'm going to present here. This image is one of my favorite Earth science images I have ever seen. I'm going to turn the lights off. Somebody put a lot of time and work and effort into making this, and it is beautiful. They did such a good job. So we have the inner core. You can see it's white hot. You have the outer core right here. You can see the outer core, these things that create the heat that it rises and then sinks. What is that called again? It starts with a C. It's a something current. Or no. It gets heated up, it rises through, and then it cools down. Blow up. Convection. Yes, thank you, Daniel. It is a convection current. You can see the convection currents in the outer core here. And then we have the mantle. You can see that it's made out of rock. It's very hot. It glows a little bit, but you can tell that it is solid. And then we have the crust. Very thin. And then you have the outer layer of the crust, or what we can see on the outside. Whoever made this did a fantastic job. I am really impressed by them. They also have the nice little detail of adding in that this map, this image of the Earth is actually quote unquote upside down again. This is Korea right here. Here's Japan, and this is China. This is the Gobi Desert. This is, seriously, like, screenshot this or do so. This is amazing.
What is the image called?
What is the image called? I don't know. Earth layer. If you just search Earth layers, I bet you can find an image of it. Nope. A lot of them are just like, oh, this one's pretty similar. That one's pretty good too. Although I don't like that this looks like painted. It's definitely not a real image. But this is pretty good. Inner core, outer core, mantle, crust. That's pretty good. Not perfect, but pretty good. Obviously, we don't have any real pictures of what the mantle or the outer core, inner core looks like, but that's what our best understanding of what it does. No, we wouldn't all die, just the people that tried to do it. Okay, now we need to just quickly finish up our discussion with the layers of Earth that are above us. What layer of Earth is above us? The atmosphere. Yep, the atmosphere. The atmosphere of Earth is very thin in comparison to everything else. The crust and the atmosphere are both very thin. This is a great image in my opinion. This is an image of the atmosphere at sunset taken by an astronaut on the International Space Station. Did you know that the astronauts on the space station get to see 19 sunrises and sunsets every day?
Wow.
As they go around the planet, they go around every 90 minutes, and they're traveling at 27,000 kilometers an hour. Pretty cool. Anyway, so very thin layer of Earth here. The atmosphere. Do you need to know these layers? No, you do not. You do not need to know the names of the layers of the atmosphere. Suffice it to say that the layer of the atmosphere closest to the Earth is called the troposphere. Above that is the stratosphere. Above that is the mesosphere, and above that we have the thermosphere.
How high do the nukes go up? Too high.
The nukes? What in the world are you talking about? Like,
Nuclear missiles.
how high do the... So when nuclear missiles are fired, they go up out of the atmosphere, and they come back down.
So they have less speed.
Well, speed is one thing, but it's easier to travel through a vacuum than it is through atmosphere. So if you launch a missile up out of the atmosphere and then allow it to travel to its target in space and then come back down, that's the best way to do it. Okay. We live here. We live at like We live at just over 1 kilometer in altitude. No, wait, no, we don't. Yeah, it's about 1 kilometer in altitude here in Ogden. Mount Everest is 5 kilometers tall, or 6, 5 or 6, something like that. Commercial plains, which is the highest that any of you have been, go up to about 10 kilometers, a little bit below that. Just barely high enough to fly over the Himalayas and other tallest mountains in the world. So everything here is just really thin air. And it just, and it just gets thinner and thinner and thinner as you go up. Very, very thin. And then the official border of the atmosphere is at 100 kilometers up. It's called the Kármán line. That's the line where space and Earth meet. Okay? Pretty sweet. All right, so those are the layers of the Earth. Are there any questions before we move on from that? Negative. Okay. All right. We are going to leave it at that then. And then I'm going to stop this.